No one knows. I thought everybody would know. That's a big gap
Oh
there.
wait, it's like cosine.
What'd you say?
What are you asking?
Oh yeah. Do you want like letters and stuff? So if I call that O and I call that point like A, the point 1, 0, and I call that point B, what's AB?
Tan theta. It's tan theta, yeah. Because it's 1 over cosine theta times sine theta. Because they're similar.
Yeah, it's definitely tan theta, right? Yeah, everything he's saying is right. I guess I wasn't planning on spending any time on this, but I guess I have to. What's the tangent of theta is like, I guess just opposite over adjacent, right? So if let's just temporarily call that segment AB, let's just temporarily call that x. So what's tan theta? Tan theta is x over 1. Everybody with me? Okay. So yeah, didn't you do this? Didn't you do this with Giles? Did you draw this picture?
No.
This is the proof. This is the proof that tan squared plus 1 equals secant squared. Because OB is secant squared.
But it was like,
You did it for like a second, like a long time ago. Anyway, if you take the secant of theta is the ratio between the hypotenuse and the adjacent. So thus OB has length secant, but that's not relevant right now. But anyway, that's the proof that tan squared theta plus 1 equals secant squared theta. Anyway, this is why we call it tangent. Has anyone ever wondered why there's like a tangent to a circle and there's also tangent line in calculus and there's also some function called tangent? It's called tangent because it is the segment which is tangent to the circle, blah, blah, blah. Okay, one more segment which I'm going to draw is this one. Alright, and now I'm going to make a claim. The claim that I'm going to make is a claim about areas of triangles. The claim I'm going to make, I think I need, so 3 colors. The claim I'm going to make is that this triangle, I guess I should have like letters and stuff. So that's AB, let's call that point C. So the claim I'm going to make is that triangle OAC, which I'll now outline in green, that its area is smaller than the area of this, what's it called, sector of a circle, which is in turn less than the area of triangle OBA. Are you pretty convinced of that fact? You must be convinced of that fact in order for us to proceed. So I'll just like kind of redraw that out or whatever. So this is my claim. It's a claim. It is a geometric argument via areas, which says that the area of the triangle with dimensions, that's 1, that's theta, and the height of the triangle is sine theta. That the area of that is, well, I'm going to say less than or equal to, because who knows what happens as theta goes to 0. But if you don't like that equal to, then just ignore it, because, if you think it's less than, then less than or equal to is also true. Is less than or equal to the area of the sector, and the sector is the one where that's 1, picture's a little bit bad, and that's theta, and that's theta, which is in turn less than or equal to the area of the big triangle, where that's 1, and that's theta, and that's tan theta. Do you all agree with this claim?
Yes.
Okay, good. All right, now we can do some math. So what is the area of this triangle?
1/2 sine theta.
Yeah, this is the easy part, right? We can just do base times height. This is going to be 1/2 base, which is 1, times height, which is sine theta. Okay, gotta go a little fast here. What is the area? Let's skip to the second triangle. What is the area of the second triangle?
1/2 tan theta.
1/2 tan theta. And now now we have to do some basic geometry. How do you find the area of a sector of a circle?
Isn't it really
So fraction between-
It's all just like proportional and stuff, right?
Yeah, theta.
So yeah, let's just be smart. What's the area of the entire circle if the radius is 1?
Wait, pi r.
No, pi
Squared. What?
Okay, yeah, what's the area of a circle with radius 1? Pi, because it's like pi r squared, but r is just 1. So the area of the entire circle is pi, but of course it's not going to be all of it, it's just going to be some of it. How much of it is it going to be? It's theta over, except not 360, 2 pi. Yeah. So if 2 pi is the total number of radians in a circle, and we're measuring theta in radians, then the fraction that theta is of the full 2 pi radians, it's that fraction of the area of the circle, which is pi. Is everyone okay with this? I'm going a little fast. All right, so I get this like beautiful formula. The pi's cancel, and what I have is this equation: sine theta over 2 is less than or equal to theta over 2, which is less than or equal to tan theta over 2. Are you impressed? Whoa, I'm in the way. What now?
Times 2.
Times 2. Genius. Yeah. All right, so Calvin, this entire complicated picture and diagram and argument has all been simply for us to rigorously establish this fact. There's just no other way to do it, right?
Yeah.
And I could hand wave that this was in fact true, but this is a proof which comes directly from the very definition of sine theta and tan theta. All right. As long as you accept this inequality, now we can do something brilliant. Should I remind you what we're actually trying to do?
Yes.
We're trying to prove that the limit as theta goes to 0 of sine theta over theta is 1.
But what if
How is this inequality relevant at all to that?
What if theta is pi? Then it's not equal to 2.
Well, I don't care if theta's not pi. Theta's near 0.
Oh, okay.
Yeah, Caleb. Your name's not Caleb. Calvin. Your name's not Calvin. Yeah, Calvin. Yeah, Calvin.
You could do that like prisoner's sandwich theorem for the theta, so you can figure out for the limit of sine theta over theta.
Well, almost. You're on the right track. The squeeze theorem is relevant, but first we need to like make the correct sandwich. Alice.
Divided by theta?
I don't think I want to. Do I want to divide by theta? Not yet. I don't want to divide by theta either, because I want the thing that I want to squeeze needs to be in the middle. Yes. Yes, Samin, yes, that is correct. What we can do is we can divide all 3 sides by sine. And let's, by the way, can I just cheat a little bit and can I just call this 0 plus? So I don't have to like deal with annoying inequality features. And then this function's like even anyway, so whatever it's doing on the right, it must do on the left. So let's just call it 0 plus. So if it's 0 plus, then sine theta is positive, and so I can just divide through by sine theta. So if I divide through by sine theta, I get 1 is less than or equal to theta over sine theta, which is less than or equal to, what's tan over sine?
Secant.
Yeah, I'll just write it as 1 over cosine, but yes, it is secant. And now, one more step.
Flippy,
Flip.
Flippy, yeah. So we can reciprocate, and if we reciprocate, we get 1 is greater than or equal to sine theta over theta, which is greater than or equal to cosine theta.
Oh, these are cool.
Awesome. Oh, I'm scared of less than sign, so I'll rewrite it one more time as cosine theta is less than or equal to sine theta over theta, which is in turn less than or equal to 1. And that is the crucial inequality which I needed to establish. Because what is the limit as theta goes to 0 of cosine theta? 1. And the limit as theta goes to 0 of 1 is certainly 1. And so as the left guy and the right guy are both going to 1, the guy in the middle must also go to 1 by the squeeze theorem. Are you impressed? Okay, I'm too lazy to write that all out, but you should. Good. I am so happy. This is a very important limit. It is, in fact, the limit which tells us what sine is doing, how sine is sort of related it tells me something about the sort of rate at which sine is growing at 0, which enables me to learn about the rate at which sine is growing anywhere else also. This is the key limit in which all other calculus-based analysis of the trig functions sort of emerges from this. Let's do another one, which is closely related. What is the limit as x goes to 0 of 1 minus cosine x over x? Okay, see if you can figure that out. Ooh. Said somebody smart, perhaps by accident.
Yeah.
One minus cosine squared or something like that. Or something like that.
What's up as a
Conjugate would give us minus cosine squared over x over x equals 1 plus cosine x. And 1 minus sine squared.
If you try to just casually plug in 0, you get 0 over 0 indeterminate, which means back to
That
work.
works, you're right. That works. I'm pretty sure.
Ooh. Actually, this is a good opportunity to share lots of wrong answers and why they're wrong.
Oh my gosh.
So, wait, you actually did this almost right. It's looking very tricky.
Oh, 1 minus cosine x, isn't that like,
Send it back to this. You went from here to here. Obviously not correct.
Then you know what minus that.
Oh, 1 plus.
Yeah.
Oh yeah, that equals sine x over x times. No.
Yeah, so a lot of you are you guys are just experienced trig types, and thus you have, wait.
No. Wait. 1 minus cosine squared.
oh, no, sine. So sine x.
Wait, maybe you're right. No, I think you're not. So yeah, some of you are realizing that I should multiply by the conjugate, because the only thing I know is this what you guys more or less all did? Yeah, so if we multiply by 1 plus cosine over 1 plus cosine, what happens now?
You get sine squared.
I get the limit as x goes to 0 of, now on the top is 1 minus cosine squared, which is sine squared, right? So I get sine squared x over x times 1 plus cosine x. Okay, I saw that on many, many, many of your papers. Sandeep, now what?
Well, maybe do like sine x over x times sine x over 1 plus cosine.
Yeah, that is exactly correct. I see something here. Now we're going to use a limit law, and the limit law says that you can split up a limit of a product into the product of the limits, provided both exist. And I don't know if both exist yet, but I'm going to just hope for the best and see what happens. And if I split this up like so, then well, now I can compute these and see what they are. What is this limit?
1.
1. What is this limit?
1.
0. 0. 0.
Yeah, by direct substitution, this is just 0 over 2. So this is just 0. Okay. And so these limits both do exist, thus retroactively justifying my step of splitting them up. And the answer is 0. Cool? Cool. So, yeah, there's some 0. It's pretty fun. So this is another really, really important limit. Our book makes a big deal out of this limit and gives you some stern warning, like, this is a limit you should know, or like, memorize, or just recognize, or whatever. So maybe you can, like, I guess I feel that way too. All right, good. That concludes that little lesson. We now have 10 minutes, in which perfect amount of time, / ridiculous amount of time, to introduce the new section, which is one of the fundamental ideas. You thought I was going to say quiz.
Yeah.
There will be a quiz soon.
No.
To introduce one of the fundamental concepts of calculus, which is continuity. I've definitely given this lesson before in 3 minutes. I definitely have a memory of giving this lesson in 3 minutes. So 12 is going to feel, going to feel, I can relax. All right. What is continuity? Well, yeah, you tell me first of all. What's the first time you ever heard that you used the word continuity? Yeah, Calvin.
Today.
Today? No, definitely not. Definitely Giles talks about continuity, but perhaps even like your middle school teacher talks about continuity. I think they do this like stupid thing called like it's called back mapping. Here's what they do. They've decided that now I'm just wasting time. But we're gonna definitely run out of time now because that's always what happens. But they do this thing called back mapping where they take complex calculus concepts like continuity and they've decided that every student must must finish calculus by the time they finish high school. So instead of teaching them useful things like arithmetic and how to add and subtract like negative numbers and fractions and maybe like times tables and algebra skills, instead they just decide we need to start talking about continuity in like algebra 1 or we'll never be able to understand it. Okay, so they teach you this, I think they teach this in algebra 1. Does anyone remember learning about this in algebra 1? No. What's the definition? Arun does, maybe they stopped. Arun, Samin?
Like if you don't have to pick
up your pencil. Oh, yeah.
Yes. A function is continuous, says Algebra 1 teachers all across the country, if you can draw it without picking your pencil up off the paper. It's brilliant. I love it. Rigorous mathematical definition. Okay, in pre-calc A, you have a new definition of continuity. What? What?
Like go and then you can like draw an open circle and then you can keep going.
Yeah, there's definitely there are many problems with that definition, which makes it not a definition that we want to adopt. Okay, now we should focus now. I'm going to do something different now. Now I'll give you the definition which I give when I teach functions to the 9th graders. Here's what I tell them. F is continuous at x equals a if and only if the following. Okay, and note that I am now doing something kind of different. I am not defining what it means for a function to be continuous overall. I'm telling you what it means for a function to be continuous at a particular point. And here is the idea. This is the general idea. I think first, it's best to talk about what it means for a function to not. Well, okay. I'll just get right to it. So if a function is continuous, then this is what I tell the 9th graders. A function is continuous at a point if it does what it promises it's going to do.
What?
Okay? So for example, as this function is getting really close to A, this function is looking like its answer is going to be L when it gets to A, right? So it's promising you that it's going to be A. And then, indeed, when it gets to A, what is the actual value of the function? L. This function is doing what it promises to do. Whereas a lying cheating function will appear to be promising that it will be L when x gets really close to A, right? But then at the last second, Lucy pulls out the football and you just suddenly the function is actually M. This function lied to you, okay? So that's what it means for a function to be continuous. It does what it promises to do. Yes?
Except what if it's like 1 over x squared, where it looks like it's going to infinity and it actually goes.
Okay, good. Hold on. Let's get to the actual math now. So here we go. Here is the definition of continuity, which I'm going to break down into 3 separate points, but really it's just one thing. Wait, can I just teach?
Yeah.
Okay. So I am continuous at a point if and only if three things must hold in order for me to say that a function is continuous somewhere. The first thing is that the limit as x approaches A of this function must exist. Okay. Furthermore, not only must the limit exist at that point A, but also the function must be defined at A. So you can just write f of a exists, or you can just say f is defined at a. And furthermore, those two numbers must be the same. So furthermore, the limit as x approaches a of the function has to be the value of the function. In other words, the function does what it promises to do. Okay, can we look at 5 tiny pictures? So, I will now draw 5 tiny pictures. All right. First, let's draw this function. Okay, is this function continuous at x equals a, intuitively speaking? No. Can you guys see? Right vision, is right vision's head in the way? Arun's like zoning out. Arun, is his head in the way?
No.
Okay, good. All right, so let's go through the bullet points one at a time. Does this limit exist as x approaches a?
No.
No, this limit does not exist. Is this function defined at x equals a?
No.
Also no. Okay, so just forget about that. All right, let's draw. Is this okay? Let's do a new one. Now I have a function which looks like this, and this is a. Is this function? Does this function have a limit as x approaches a?
No.
No. Is this function defined at x equals a?
Yes.
Yes, but it makes no sense to ask the third question because the first question's not even true. Okay, now here's a new example. Now I have a function which does like that. Does this function have a limit as x approaches a?
Yes.
Yes. Is this function defined at a?
No.
No. And thus it makes no sense to ask any follow-up questions. Okay, we're getting warmer though. Now I have this function. Wait, yeah. Here we go. Is this function, am I going too fast? Does this function have a limit?
Yes.
Yes. Is this function defined at x equals a?
Yes.
Yes. Are those the same numbers?
No.
No. All 4 of these are discontinuous for slightly different reasons. And finally, happy time. Does this function have a limit?
Yes.
Is this function defined at a? Are they the same number?
Yes.
Ta-da! Therefore, this function is continuous. All right, that is continuity. Question?
Is like y equals absolute value x continuous?
Sure. She wants to know about the function f of x equals absolute value x. We have to ask me at a particular point.
0, 0.
Yes. Is this function, so is f of x equals absolute value x continuous at x equals 0? I don't see why not. What's the limit as x approaches 0?
They're all 0.
It's 0, and the value of the function is 0, so everything's good.
Good afternoon, staff and students.
Oh,
This
fuss.
is Mrs. Johnson, your
No, not Whoa.
I just want to let you know that yesterday after school, a student was leaving the building and she was approached by a male who grabbed her arm
Oh, no.
and then proceeded to slap her on her leg. The student was able to break free from this adult male and come back into the building. Students, as a result, we have sent letters by ConnectEd to your families about this incident. We also, have spoken to the student and a police report was taken to make sure that we find this person who did this. I just want to let you know, students, that when you are around the school grounds after school hours, please stay close to the building, and also if you can be with a friend, that helps as well.
Buddy system.
And please let us know if you see anyone behaving in a suspicious manner or anyone who looks like they shouldn't be on school grounds. Please let any staff member know. Again, letters were
I'm wearing a
sent by
tie.
ConnectEd. I want
Very
everyone
tight, you can do anything.
to be safe as we're coming later.
Oh my gosh, the video.
If you have questions about it.
Okay, good. Wait, not to what?
The video is.
Or,
I know the video is just gonna have this weird
um,
thing, whatever.
Thank you, students.
All right.
And I want you to have a wonderful weekend.
What?
You should probably tell them like this.
To pause it? I considered that.
No, no, no.
What?
You should just cut this section
You should just cut
out.
this, no, this is a no editing production. Alright, the last thing, and then I think I'm actually gonna end early. The last thing is, that this definition tells you what it means for a function to be continuous at a point. But in Algebra 1, they never talked about continuity at a point. They always talked about a function is just either continuous or it isn't, right? So once you understand what continuous at a point means, then it becomes possible to define continuity over an interval. So here comes my definition. F is continuous on the open interval AB if and only if what?
For all x between a and b, that happens.
Yeah. If and only if F is continuous at x equals c for all c on the interval AB. In other words, once I know what it means for a function to be continuous at a point, Matteo just says, duh. Well, if you're continuous at every single point of an interval, then we say that you're continuous over the entire interval. Okay, are we cool? All right, good. Homework will be in the book. Oh, by the way, all of period 3 is going to be watching this video this weekend. Maybe I should have told you that at the beginning, because to make up for their snow day, which I'm sure they will enjoy. So your homework is going to be from the book, and also you're going to finish Limits Review Worksheet 2. Any questions? All right, we're almost done with this unit now. I'll see you guys later. Turn off. All right, that ends lecture 4. Bye.